Good morning, good afternoon all, and welcome again for this lecture of electronics, in which we have studying digital electronics, paper two, semester two of RTM Nagpur University Nagpur. And today we are going to continue with the same sessions, and we will continue with the new topic of Unit four of semester two, that is the memory organization. So let us start with that, and yeah, I guess my screen is visible to you, and yeah, let me introduce myself. Myself, Dr. N.D. Meshram, Head and Associate Professor, Department of Electronics, Sri Mathura Das Mohta College of Science, Nagpur. And today we are going to study the memory hierarchy and cache design. Right. So we are going to study the memory organizations in all. So let us begin with that. Now, this is actually the paper two, which is of semester two, and it is unit four, which comes under this memory and storage circuits. Okay, so we will work on this. We'll study on this. Actually, we have the basics of it. We have studied the registers, and we have studied the shift registers and all. The registers are supposed to be the one-bit memory device. Though. So the flip-flops are also called as the one-bit memory device. So memory is something where we need to store the data. Now, in the situation where we study digital electronics, which implies that we are going to store the digital data, right? So how we organize the memories, how what are the configurations of those memories? That is what we are expected to study in this lecture today. So let us begin with that. Now, the first is how what we are going to cover in this topic is in the whole in 2 3 lectures that we are going to proceed from today onwards. So overall memory chip organization, static memory circuits, that is SRAM, static RAM, dynamic RAM, then sense amplifier circuits, then the row address, implementation of CPU registers via flip-flops, fast transistor logic, read-only memory, and so on. So we'll be continuing all that. Let us start with this. The first topic of today, that is the memory hierarchy and cache design. Now, what are the requirements of that memory? That is what we need to understand first. Let us go with that. What should the memory consist of? So memory should have the performance. Now, what type of performance we are expecting to require? That is actually the access time, which means that the time between presenting the address and getting the valid data. So whenever we want the data from the computer or say PC or the CPU, then what we do, we give the address that the data is stored somewhere there. So the data is to be taken from that particular address that is actually given by the processor, right? So the time lag, as soon as we are giving the address and we are receiving the data, that particular time is called as the access time. So remember these some of the technical words, because these are very important while we consider the memory, right? So access time, then we are having the memory cycle time. So memory cycle time is nothing but the time may be required for the memory to recover before next access comes. So as soon as you have given the address and the data has been reached to us, then for the next data, the memory should again refresh itself and get ready for the another address line, so that the other address should other data should be kept to the user, right? So that is that memory cycle time, and the cycle time is access plus the recovery. So this is in total we call it as a memory cycle time. Then the transfer rate. Yes, this transfer rate is very important. The rate at which the data can be moved. So the data can be moved from say the CPU to the memory, or from say memory to the CPU. So that is called as the transfer rate. So that should also be the basic structure of the memory. What are the physical types of memory? Now, what type of memories are available in the market that we are going to study? These are some of them are semiconductor memories, in which we have RAM, that is random access memory. We'll study this in depth. Then we are having magnetic memories. You have disk and tape type of a memory. So earlier there were the cassettes, right? So those are called as magnetic. Then we are optical. Optical, you know that CDs, DVDs, and say in that case our hard disk is one of the optical memory device. Then others we are having that as bubble and hologram. So these are all types of memory where we are expected to store some digital data or some data, right? So the main important job of a digital electronics, the main purpose of application of the digital electronics is that we are able to store this huge amount of data at a very small place, small say area, right? So that is the main crux of digital electronics, and that is where we expect that digital electrons should be applied. So the memory plays a very important role as far as computers or microcontrollers are concerned. So everything should be there intact, and that should be very low cost and say in having very less time. Some of the physical characteristics, that is what I was expecting to tell you. The decay time should be low. Volatility means whether the data is being retained in that memory or not, if the power supply is switched on or off, right? So it should retain the data, that is volatility. We'll study this. Then erasable, so we can rewrite the data. We can rewrite the data in that memory. It should be erasable, and the other data should be say saved over there. So in CDs, as you are able to, so if they are rewritable CDs, then it's okay. But if they are not rewritable CDs, then once you write the data in that CD, then the CDs are not being reused, right? So that is what erasable means. That the memory should be, the data should be erased, and the new data should be copied onto it. So the power consumption is, yeah, is the most important, that it should consume the less power comparatively to the other devices. So these are some of the characteristics which are physical characteristics which are essential. Then the organization. So the organization, that is the physical arrangement of bits into words. So the data is to be stored in form of ones and zeros. So ones and zeros are said to be the bits, right? Now these bits are stored one by one, and now they are being formed as words. So as you know, I've told you in the earlier classes that single is called as a bit, 4 is called as a nibble, 4-bit is called as a nibble, 8-bit is called as the byte, and 16-bit is called as the words, right? So as you go on, as you go on say increasing the bits, then it forms a word, right? So 16 bits is called as a word. So when you go on saving the bits, so one by one you are going to save, and how much bits you are able to save in that particular memory is called as the physical arrangement of that bits. Now how they are being arranged accordingly, because we are expected to retrieve that data also. So it is not always obvious that everywhere we are going to use the same technique to store the data. So there are some more ways of that. So these are the example that is interleaved, and some portion is. But the bottom line which is there is how much capacity it is having. So the main purpose of memory is we require the highest capacity. As you are able to see, if you go to purchase a mobile phone right now, so it is costing with the range of how much capacity of how much say memory you want in that mobile, right? So as you go on increasing the memory capacity, then the price also increases. Second one is the fast. How fast it is, because time is money. So we need that my memory should be very fast. So as soon as we expect, the data should be delivered to the CPU, or the data should be taken from the CPU. The time which is consumed over there should be minimum, right? Then how expensive? The cost is very important over there. So cost factor is also there. So these are some of the bottom line which we are expecting when when we need some memory to employ somewhere. Now, this is the most important part, that is the hierarchy of hierarchy list, or the hierarchy of a memory. How the memories are being organized accordingly. So let us see. This is what I am showing you the list. I am going to show you the hierarchy also. So the list says that we are having the registers. Now registers, we have studied registers. Now these registers are inside the microprocessor itself. Registers are called as the general purpose registers, CPU, right? In central processing unit, that is the microprocessor, or say the microcontroller, it itself consists of these general purpose registers, where we can have a 8-bit, 16-bit registers, as well in the microprocessor itself. Now you'll study this in final year, that you'll be having uh, 6 or 8 type of a general purpose registers in a microprocessor 8085. Uh, Say register A, B, C, D, E, and HL. So we are having this registers 8 bit, where we can use those registers for temporary storage and for say the processing of a data, right? So these are called as the registers. Then we are having the cache memory. Now the cache memory is divided it again into 3 parts, that we are having L1 cache memory, then L2 cache memory, and then the main memory, right? So there is one more, that is L3, but it's okay. Now L1 and L2 are the cache memories. So what are these cache memories? So these cache memories are very nearer to the CPU, so that they are able to be accessed easily by the CPU, right? So that is why they are called as cache memory. They are very small in size. We'll study this cache memory in depth. Then we are having the main memory, right? So the main memory might be the say where we are expecting to store, that is RAM or ROM. So main memory is there, then disk cache, that is hard disk, that disk, that is say the CDs and DVDs, then optical and cell tape. So the hierarchy goes like this. Hierarchy means the arrangement of the memory to which we are going to set. So we are having registers, L1 cache, L2 cache memory, then main memory, disk cache memory, then disk and optical and tape. So this is like the list of that, and we'll study this list again as you will understand this. So you want what you want. It is possible to build a computer which uses only static RAM, right? So we'll see this in later portion, why we calling it like static RAM, and this would be very fast, and this would need no cache. How can you cache a cache, right? And this would cost a very large amount. So this is actually a concept which is given. If you are not using a erasable memory, then you are using a static memory, which is not going to change. And if it is not going to change, which implies that it will be very fast, and it will not it will be very fast, but it will be expensive, and we will not be able to change, right? So we need this type of a structure. Now let us study the hierarchy. So during yeah, so this is something which we'll study now, where we are right now. So we are having these 5 classic components of a computer. That is, memory is usually implemented as dynamic RAM, that is dynamic random access memory for main memory, and then static random access memory, that is for cache memory. And this is the block level structure of say the CPU, right? So CPU is having the processor, then it is having the control over everything, then the data part, that is the buses through which we are expected the data to be transferred from the CPU to the memory, or say the input output device, right? And the memory is in between, so where we are expecting to store the data. This control is going to control over everything: the processor, the data part, the memory input and output. So these are called as input devices, and these are output devices. Input output devices are like keyboard, mouse, and wherever we are expecting the data to be inputted to the computer, that is called as the input device, and where we are expecting the result to come, that is called as the output device. Okay, so these are the 5 classic components of a computer where we require this: the processor, which is nothing but the control and the data part, then memory, and the input output devices. The memory is usually implemented as the dynamic RAM, that is for the main memory, and static RAM, as called as the static random access memory for cache, right? So this is the basic 5 components in a computer. Now let us see the uh, yeah, what are the capacity of that. So this is the capacity, that is 2 into in 3 years, that is this is the speed latency, this is the logic there, and this is the DRAM that we use. These are the data that we need, that this is how we have increased the size of the memory, and we have decreased the uh, time access time, right? So as you are able to see, this is the 100,000 is to 1. In 1980s it was only 64 kb. I guess I don't have that picture, I would have to search somewhere. I have that picture with me. I will say show you that how much capacity was there in single memory device which was invented that time in 1980s, right? So this was around say 64 kb right now, and now in 1995 it is around 64 mb, and still it has been increased. And if you see that time, say it has been increased to 2:1, right? In 1995, now it is at very high speed. So we are working in gigahertz and all. So this is the ratio. And yeah, just as say the Moore's law, where we have seen how there is a development of the memories, right? So this is not in your uh, syllabus, but just need to show you that this is where we have progressed so rapidly that the DRAM has been increased in 9% and this has been increased in 16%, right? This is 16% per year. That is the performance of that. So depending on the years over there. So how we have progressed in the development of memories, and that too in DRAM. Then hard disk. We have seen this hard disk. This is where in this say CPU box where we are expected to store the main data of a computer, right? So that is the hard disk. This is the magnetic disk, and this is the read-write head, which is revolve. This magnetic disk is revolving at a very high speed, and it is having sectors, right? So we are having sectors like we have pizza. So pizza pieces like we are having sectors over here, and these sectors store the data, right? And this laser beam read write head having laser is able to say sense the data, and it is able to write the data as well as read the data from that. So this was just an example. So let us start with this memory hierarchy. So memory hierarchy consists of memory technologies, that is having typical access time, that is and the cost. So the static RAM, that is the access time which is having around zero point 0.5 to 5 nanoseconds, and the cost is around say 4,000 to $10,000 per GB. That was in 2004, and we are having dynamic RAM. Now it is less. Dynamic RAM, the access time is around 50 to 70 nanoseconds. The cost was around $100 to $200. Now it has been very decreased. Then yeah, this is what the hierarchy shows. We are having this hierarchy. So level 1, level 2 up to level n. Here we are having the memory which will be increasing, and increasing distance from the CPU in access time. So we are having a CPU on the top, and it is being say we have a pyramid like of a structure. This is the size of the memory in the bottom. So as you go on increasing the distance from the CPU, the size of the memory increases, right? So we are having this. I will show you again, and this is how it goes. So it goes from the processor to say the nearest memory device, that memories which are cache memory and say general purpose registers, and then to the main memory or say the last level memory. There the data is being transferred, right? I will show you that hierarchy. So this is the computer. The storage system is organized according to the following hierarchy. So this is the hierarchy that we are expecting to take, and yeah, I guess it is visible. So again, if you see, we have just rotated it. So the top portion is now having a very high capacity, but again the distance from the CPU is very less, right? So we are having this archive storage, that is magnetic tape or photographic, then moving head disk that I have just now told you, high speed drum, then charge coupled devices, main memory, cache memory, and then internal memory. So we are increasing, decreasing the cost and increasing the decreasing the access time, right? So this is how we are having the. I will show you one more diagram on that. So yeah, uh, yes. So this is the hierarchy of that. So as you are able to see, the registers are on the top, which are very nearer to CPU, and the cache memory and then memory. They are all stored in the inboard memory, right? So they are situated near to the CPU. They are having the less access time. Okay, but they are very costly. So as you go on increasing this nearer to the CPU, the cost is also increased. So instead in that, the speed access time also decreases. But yes, they are inside it. Then the magnetic disk, CD-ROM, CD read-write, DVD read-write, DVD RAM, they all are outboard, means they are not situated in the motherboard. These are stored in the motherboard. Registers are inbuilt inside the microprocessor itself. The general purpose registers are being accessed and are being used by only the CPU processor only, right? So nobody other can be used. Yeah, we can program the CPU, we can program the microprocessor to use those general purpose registers, no doubt in that. So registers are there. Then we are having some cache memory, which is very inside the microprocessor. Some cache memories are inside the microprocessor, which we call it as L1 cache memory, and some memories are just outside but very nearer to the CPU, right, to the microprocessor IC. That those are called as L2 cache memory. So I have told you the L1 cache memory and L2 cache memory is over there. Then after that we are having RAM, and after that we are having the main memory, which is hard disk and all, right? So this is again the hierarchy list I've shown. Then we are having the magnetic disk and magnetic tape type of system. So this is the hierarchy that we need to understand: registers, L1, L2 cache, and main memory, then disk cache, then this optical tape, and so on, right? So this is actually the hierarchy of the memories that are implemented inside the computer. Okay, then memory speed. So access time, the average time taken to read a unit of information. Example, 100 nanoseconds, which means implies that 100 nanosecond means 10 into 100 into 10 raised to power minus 9, right? Seconds. 10 raised to power minus 9. This should come in the power. So nano means 10 raised to power minus 9. Okay, you should understand this nomenclature also. Micro, milli means 10 raised to power minus 3, micro means 10 raised to power minus 6, nano means 10 raised to power minus 9, and pico means 10 raised to power minus 12. So the second of 10 raised to power minus 9. So this is the smallest portion of the time, which is the access time. Then we have access rate, that is nothing but equal to 1 by TU. That is nothing but the frequency, right? So we are having the 10 megabits per second frequency over here. Then cycle time. So both are there. The average time lapse between two successive read operations, that is 500 nanoseconds, means 500 into 10 to the power minus 9 seconds, right? So this is cycle time. Then bandwidth of or the transfer rate, that is 1 by TC. RC is equal to the 1 by TC. Again, it is a frequency, that is bits per second. How much bits we have transferred per second, right? So this is the memory speed that we have, and the example is shown 1 by 500 nanosecond, that is equal to 2 megabits per second. Okay, now classes of memory. This is what we are going to continue in the next class. So classes of memory are RAM, that is the normal memory. We call it as a random access memory. So we can access this memory randomly, anytime, anywhere, right? But it is again, say, the volatile type of a memory. Then we are having direct access storage, that is hard disk, CD-ROM, DVD. Then sequential access storage type, that is DAT. Then associative addressable memory, searches for data via bit patterns. CAM, that is content addressable memory. We don't have this in our syllabus. This includes comparison logic with each bit of storage. A data value is broadcast to all words of storage and compared with the values here. Then words which match are flagged, and subsequent operations can then work on flagged words. And these are used in computing dictionary. The free this can be accessed from this. So this is some classes of memory that we are having. We are concerned with this both. So we will have static RAM and dynamic RAM. We study in depth. Okay. So yeah, so I guess we will be studying this in the next class, cache and main memory. But we can have this block diagram. Will we understand what is cache memory and what is, say, the main memory, and where they are being situated, how they are having the organization of it, right? So here we are having the CPU. CPU means where the microprocessor is situated and where the actual processing is supposed to be done, right? Sorry. So whenever what it implies is whenever I need to say work on that, work on the PC. So whatever I am giving you the input, now this input is first given to the CPU to say interpret it. So what you have done, that is to be interpreted. So that job is done by the CPU, right? And then this CPU is going to store that data into this memory. Now, as you are able to see over here, it is the cache memory is very nearer to CPU. Sometimes it is inside the CPU. So I have told you that the cache memory are of three types. Now, what is actually the cache memory? Now, cache memory is something which is easily accessible by the CPU, which is, I have one example to tell you that if I need to purchase something, I want some money. So where I am going to search first? So I need to search that money in my packet first. So which is very close to me. So what I will do, I will go in my packet in my purse and I will search the money. Okay. And if I need more money than what I have in my purse, then what I will do, I will go to say my cupboard where I store or where I have a say some amount of money where which I can use, right? So that is the main memory. And lastly, if I require more money than that, then I will go to the bank, right? So this is how we can explain the cache memory is very close to here. So we are having three levels of cache memory. The first cache memory, that is L1, is situated inside the microprocessor itself, where this memory can be accessed directly by the microprocessor inside. Then we are having level 2 cache memory. Again, it is nearer, it is outside the microprocessor, but it is very close. So the microprocessor can easily access that, right? So we can say here in that case, the level 1 cache memory is nothing but the register, general purpose registers, which it is accessing and which the CPU is going to use it for processing, right? The second one is the memory, which is again used for the memory, again used for the storage or read of data, which is very close to CPU, but not inside the CPU, right? It is not inside that microprocessor, but it is just outside the microprocessor. But yes, it is inside that, nearer to the CPU. Again, the level 3 cache is outside the CPU itself, and it is a little bit at a very distance, but it will have a very high speed address line, right? So it is connected with a very high speed address line over there. So these are the cache memory which are very close. So what I have told you, if I need some money, so I will just go to the purse. So it is very close to me. Then I will see the cupboard. Then I will say safe where I have putting some money over there, and then I will go to the bank. So accordingly, I will have these three classes of cache memory, and we are having a main memory. I guess you have understood this. What is actually the cache memory? So I guess uh, up till now it's okay. So we'll continue this memory in the next class, hopefully day after tomorrow. Okay. So if you have any questions, you can ask me on this. So this is what we have studied today: the memory organizations and some important characteristics of a memory. Yeah. So yeah, today we have started with memory organizations. This is actually the unit 4 of semester 2, paper 2, and this is what we are expecting to complete. These are the performances that we require. Then this is the physical, yeah, access time, memory cycle time, then transfer rate. Uh, then we are having the physical types. These are semiconductor, RAM, magnetic, disk type. These are examples of that. Others, that is bubble and organ physical characteristics, decay, volatility, erasable, power consumption. Organizations, these are the how the bits are being arranged into ones, right? So that is the bottom line, how much capacity we are having, how fast they are, because time is money, then how expensive they are. Then the hierarchy list that we are having, first we are having registers, L cache 1, L1, L2 cache 1, then main memory, this cache, this opticals. So we need this type of characteristics. Then, yeah, these are some of the five components which are in the CPU. This is the old data that we have having. This is the graph. This is the hard disk. Then this is the hierarchy. And here, this is the hierarchy that I need to show you. And This starts from the internal, then cache, then main memory, charge couple, and high speed RAM. And as you're able to see, this is moving towards up, that is decreasing cost, and again this is decreasing the access time. So the internal memory is very close to the CPU, then cache, then main memory, then charge couple devices, CCD we call, then high speed drums, moving and ahead magnetic or optical, than say the magnetic tape and photographic. So we are having this memory organizations. Then this is the say, situation or where the memories are being situated inside the CPU, right? So it is very nearer to inboard memory, that is on the motherboard it is. And outboard storage, that is magnetic disk, CD-ROM and CD read write, DVD read write. Then offline storage, those are magnetic tape and MO and WOM. So they are all. These are again the hierarchy list that we are having. These are the memory speeds, access time, access rate, cycle time, cycle and bandwidth or transfer rate. Then classes of memory, RAM, direct access memory, sequential access, CAM is also there, and ROM is also there at the end. Then we are having, this is the arrangement organization of the memory, cache and memory, which you are able to see that CPU is, the cache memory is very close to CPU, and the main memory is very far from here. So we are having this as single cache. Here we are having their three level of cache organization. So this is actually the memory organization uh, for today, right? So I guess this much is enough for today. If you have any questions, I will be happy to answer. So you can unmute yourself and you can ask me questions on that. So thank you very much for joining. We'll be continuing this again in the next session tomorrow or day after tomorrow in the next class. Thank you very much for joining. Stay home, stay safe, take care. See you in the next class. By that time, go through my YouTube channel, watch my videos, like, share, subscribe my videos, and thank you, many. Please comment on my videos. Have a nice day. Good day.